How we doing, guys? I want to talk in this video about some of the early transmutation experiments. Now, what transmutation means is if you can convert one element into another. An earlier name for this was alchemy, which was something very close to magic. A lot of people spent a long time trying to convert lead and things into gold and never succeeded. And it was decided that alchemy was a load of nonsense. And it is a load of nonsense, but this transmutation is kind of a similar thing where Ernst Rutherford, the Kiwi physicist we talked about before for his gold leaf experiment, again playing around with alpha particles, was able to bombard some nitrogen 14 and create oxygen 17. So that was kind of the first artificial human-driven transmutation of one element into another, where he was able to convert an element, which is a pretty big deal. But the method he used, nobody uses it anymore. He was using natural radiation sources that were alpha emitters. These guys, Cockcroft and Walton, maybe did a more important experiment around the same time. Walton, by the way, was Irish. He was born in Waterford. They actually do ask about that sometimes in the exam, so worth just remembering. Walton was born in Waterford. What they did was they took a lithium nucleus and bombarded it with, that's sometimes called a proton, because a hydrogen nucleus by itself with no electron orbiting is just a proton. So that's an ionized hydrogen nucleus whenever you hear the word proton, and produced helium, okay, as well as usual energy. The how of how they did this is something that you're expected to be quite familiar with and to be able to describe. Okay, just to point out a few things here. Your atomic number here remains the same. Your mass number, sorry, is conserved. So a total atomic number of 9 there, a total atomic number of 9 on the right. On the left, a total mass number of 18, and on the right, a total mass number of 18. Same thing down here, total atomic number of 4 gives a total atomic number of 4, total atomic mass of 8, 7 and 1 gives an atomic mass 4 and 4 of 8 down the bottom. Also, energy or mass energy is conserved. So the lost mass from this side will manifest as energy on this side. And finally, in this experiment, momentum is conserved as well. That's going to be a fairly common thing, but anytime you see something being created like this, you'll often see particle pairs being created, and one will go one way, the other will go the other way, in order to allow momentum to be conserved in this interaction. So those are our three quantities. Don't forget that: charge, mass energy, and momentum, that are conserved in any one of these interactions. If I can point you to the textbook on page 368, please. We've got this diagram, or this picture, which is a pretty impressive experimental setup, which is our Cockcroft and Walton accelerator apparatus. This isn't the one they used, but it's the same type of apparatus now. We more commonly call this a linear particle accelerator these days, and this is the granddaddy, I suppose, of the linear particle accelerators, and indeed all particle accelerators. And you're expected to be able to explain how it works. So can you make sure, first of all, that you learn this diagram by heart? This is one that you could be asked to reproduce in an exam. What was happening here? Well, first of all, you've got these protons were produced in what's called a hydrogen discharge tube. So in here, you've got hydrogen. It's ionized so that it becomes positively charged, which means you've stripped away the electrons, and all you're left with then is individual protons, which will in turn respond to an electric field. So our electric field, excuse me, so our electric field then is generated here. You can see you go from about 400,000 volts down to 0 volts. So any charged particle is going to accelerate in that electric field. And what you get, and the tube has to be evacuated, because remember, these particles will be stopped by a little bit of air or something like that. So it's a vacuum inside this tube. You get this accelerating beam of protons, okay, which is traveling down this part of the accelerator, and it's striking down here a target which is made of lithium. Okay, so you get this interaction of one proton, which is our H11 in our equation, with a lithium target down here. And what was happening then was these guys were able to observe on this zinc sulfide screen here, which is what the screen here, G, is. These small little flashes, or scintillations they call them. Now, they have to look through a microscope to see this, but they could see some form of energy being released, and they were able to calculate that what they were looking at had all of the characteristics of an alpha particle or a helium nucleus. What's more, they went in opposite directions. Okay, so that's our conservation of momentum. And the calculation, or sorry, the formula, I suppose, that describes that interaction is this one here. Okay, we had lithium, which is being bombarded with this proton, this beam of protons. And as a result, you're getting alpha particles being given off, or helium nuclei being given off, as well as energy. And the other really important thing this experiment did was it was able to experimentally verify that the lost mass was being produced as a form of energy, and that Einstein's E equals mc squared calculation, which came from, I suppose, a theoretical analysis, also applied in the lab. And so that obviously gives us a very, very strong credibility. And back when this experiment was being done, E equals mc squared was not the famous equation it is now. It was a new equation that still needed to be verified. Okay, so question 2 here from exercise 32b. If a proton in the Cockcroft and Walton experiment was accelerated by 750 kiloelectron volts towards the lithium target, calculate the energy released in the disintegration and write the reaction as an equation. Now, I'm actually going to do this bit first, write the reaction as an equation, and then we'll look at the energy, again, using all these values plus the values given in 32a as well. Okay, so here's our equation, which is lithium 7 and a proton, or hydrogen nucleus, plus this energy was accelerated up with this 750 kiloelectron volts. So it struck the lithium target with that much energy already, gives us 2 alpha particles plus some other amount of energy that we still need to work out. So when they ask us to work out this amount of energy, it's still using conservation of energy. Just don't forget that you've got this energy here as well. So really these problems are about mixed units is the big trap in these problems. Other than that, they're not that bad. So let's just be careful here. Lithium mass is given in the question in atomic mass units. So it's given, sorry, as that's 7.01600 atomic mass units. The mass of a proton, you can take it from the log tables. They've given it to you in this exercise, 1.67 times 10 to the minus 27 kg. Okay, so it's given in kilograms. Electron volts is not a unit we tend to use in calculations too often. So that's 750 multiplied by the charge in the electron, 1.6 times 10 to the minus 19 joules. Okay, you've got 2 alpha particles, so that's going to be 2 times the mass of an alpha particle given in atomic mass units, 4.0026 AMUs, or just U, plus some other amount of energy. I'm just going to call that Q, which gets used for energy quite a lot. Right, so let's start off by converting this. Okay, that's going to be 7.01600 multiplied by, in atomic mass units, 1.66 times 10 to the minus 27. Again, that's either the unified atomic mass unit on page 20, on the log tables, page 47, or I'm actually taking it from question 1, which gave it to 3 significant figures or 2 decimal places there. I'm shortening it. Same thing here. This is going to be 2 times 4.0026 multiplied by the charge in the electron to convert. Sorry, not the charge in the electron, the atomic mass, unified atomic mass unit, to convert that to kilograms. Okay, so those calculations are, okay, so they're given here. This first one, so that's the mass of your lithium nucleus, in kilograms, plus that's your mass of your proton, you can write it either way, in kilograms, plus that's your 750 electron volts in joules. And that gives us, this is the mass of our two helium nuclei, helium-4, and we've got some leftover energy as well. So what we need to work out is, well, what's the difference in masses here? Okay, so if you put these together and then subtract this, you've got the difference in mass. And I'm just going to do that calculation off screen here. If you do that using my numbers, you get 2.8 times 10 to the minus 29. I'm embarrassed to say that's wrong. It should have been 3.0926 times 10 to the minus 29. And the reason I'm so far off, these are tiny numbers, it's because I've rounded far too early with a lot of my decimal places. So I'd encourage you, if you're doing these yourself, just make sure you're working to as many decimal places as you are given in calculations with nuclear particles. That shouldn't have been a mistake that I made there. Anyway, that's our lost mass right there. And you can convert that to energy using E equals mc squared. So you'll say E equals the mass there, 3.0926 times 10 to the minus 29 times 3 times 10 to the 8 squared. That will give us 2.78 times 10 to the minus 12 joules. Now that's the energy converted, but don't forget you had energy coming into this problem as well. So the total energy is that 2.78 times 10 to the minus 12 plus the 750 electron volts you had coming in, which we now call 1.2 times 10 to the minus 16. Doesn't look right to me now. Let me have a look at that again. Yeah, apologies. That should have said 750 kilo electron volts, which means 750,000. So you get times 10 to the minus 13. And that does seem right. So 2.78 times 10 to the minus 12 plus 1.2 times 10 to the minus 13 joules gives a total of 2.9 times 10 to the minus 12 joules of energy there. I'm going to leave it there. I'm going to ask you to do question. Yeah, you might try question 1 yourselves, please.